So if we use a second order Taylor expansion, or we use, for example, a trapezoidal method, then we can expect to have a higher order, okay, a higher order method for solving the differential equation. So let's use the second order Taylor expansion, for example, and see what we get. Okay. Y of xi plus h is equal to y of xi plus h y prime at the point xi plus h square over 2 y second, okay, at the point xi plus etc. Now we're gonna retain just this second order term. Of course, this is f of xi yi as we know. So h f of xi yi plus h square over 2. Okay, so this is d over dx of f of x y at the point xi. Okay, now if I calculate d over dx f of x y, okay, I'm doing the derivative with respect to x, but f is a function of two variables. So it's equal to df over dx by dx over dx, which is 1, okay, plus, okay, df over dy, okay, I should use the partial derivative if you want to be more accurate, okay. Df over dy multiplied by dy over dx. Okay, so I will note it like this. This is f prime of x, and it's the derivative with respect to x, plus here this is f prime, okay, of y. It's the derivative with respect to y. Okay, f prime of y dy over dx is f multiplied by f. Okay. So I can write this method that is based on the second order Taylor expansion, okay, as being y of xi plus h f of xi yi. Have to replace it by f prime of x, okay, at the point xi yi, okay, plus f prime of y at the point xi yi multiplied by f of xi yi. Example. Okay, so if f of xy is equal minus xy, the example that we treated, let's say f of xy equals minus xy, and f prime of x, the derivative with respect to x is equal to minus y, derivative with respect to y is equal to minus x, and then this scheme here becomes y of xi plus h is equal to y of xi plus h, okay, multiply by minus xi yi, okay, because it's f of xi yi, plus h squared over 2, okay, multiply minus yi plus minus xi multiplying xi yi. Okay, so it becomes square here. It's xi square yi. Now, the only problem is that the f prime here with respect to x and f prime with respect to y depends on the fxy. So we cannot derive a general expression. We need to calculate this f prime of x and f prime of y for each different function. Okay, so that's why we will not use this method, even though it's an explicit method and it's second Taylor expansion. But for each function we need to derive, okay, the function f xy with respect to x and with respect to y. Okay, so it is not a general approach. Instead of using the rectangle left corner approximation, let's use, okay, the trapezoidal rule. So in trapezoidal rule, basically, okay, if you have just 2 points xi and xi plus 1, then it becomes the mean value, okay, of f of xi yi plus f of xi plus 1 yi plus 1. And this is here yi plus 1. Now the only problem is that here, if f is a nonlinear function, okay, here it becomes a nonlinear equation, right? Because here we have the yi plus 1 depend on a function of yi plus 1. So we need to solve a nonlinear equation here in order to solve the problem. So this is an implicit method, okay, and it's not so convenient here okay, to solve this problem. That's why we will see other methods that are higher order approximation, but that are explicit methods and which are called the Runge-Kutta method. We will discuss the Runge-Kutta method in the next session.